The broadcast is now starting. All attendees are in listen-only mode.
Hello and welcome to today's webinar. I'm very pleased to be introducing Jack Sheldon of the Antea Group. He's going to be talking to us about safe and effective in situ remediation best practices. Just to touch on the subject without going through what he's going to talk about, Jack is the Senior Remediation Specialist at Antea Group. His presentation is discussing the Select, Design, Execute project checklist that he uses to apply remediation products safely and effectively. He uses data collection, adherence to details, and good field awareness, which are the key themes that are stressed throughout this webinar. An introduction to Jack Sheldon. Jack Sheldon, Senior Remediation Specialist at Antea Group, is based in the US. He actually studied in the Netherlands, amongst other places, and is regularly in contact with colleagues in Europe and Brazil and elsewhere. He's a remediation expert with over 36 years of industry experience. He specialized in the field application of various types of bioremediation and chemical oxidation reduction systems. His personal involvement in 22 first-type remediation projects in the US and international experience, including dozens of remediation projects across Europe. So before Jack begins, I just want to introduce you to how it'll work. Jack's going to talk for about 40 minutes on this subject, and at the end there'll be a chance to pose questions. If you do think of questions as the talk is going on, please just enter them in the panel on the right, and we'll write them down, and then I can ask Jack those at the end. If you think of questions too late and we've finished, we will be sending you an email afterwards, just looking for feedback. There's a chance there to put your questions in, and we will respond as soon as we can afterwards. If you have any problems with the sound, the best thing to do is just log off, log back in again. If it persists, don't worry, we'll be recording this and we can send you the recording. But right now, I'll hand over to Jack and I will ask questions at the end. Thank you.
Well, thank you, Gareth, for that kind introduction, and thank you to Regenesis for hosting this webinar today. And thank you to all of you that are participating today. I hope that you'll find this topic interesting and that you will ask some questions, and I'll certainly be able to get back with you and try to answer those questions to the best of my knowledge. So our topic today is safe and effective in situ remediation best practices. And often I speak on technologies or on case studies, but today's webinar is a little bit different. So we have a completely different objective than what we normally might have. And that objective today is to help you utilize a checklist tool to think through various project issues. Of course, every project goes perfectly, right? Well, we all know that that's not the case. We know that all of our projects have various issues that arise either before we initiate the project, while we're in the field, or even after we've been in the field. There can be issues that come about, and we need to think about those things and think about solutions for them. We also want to create a tool that allows our overall team of professionals to all be in agreement on what we need to do for our remediation project. And our checklist tool I'll introduce, we'll talk about that as well. And of course, we always want to improve project performance and make safety the central point of everything we do. And again, this checklist system allows you to do that with each and every project. When I refer to a checklist, it is actually an Excel spreadsheet that we use as a planning tool on each and every one of our remediation projects. It happens that we work with Regenesis and their field services group quite often, so we use it with them on a regular basis. But we also use the checklist with other contractors, with other technologies, and it fits very nicely with whatever type of remediation you're going to do. So without further delay, we will talk now about the checklist. And what you see before you on the screen is a checklist that we developed as a team here at Antea Group. And we use this as our planning tool for our projects. If you look at the blue box in the upper right portion of the slide, you'll see that it's divided into three sections: select, design, and execute. And those are the three critical phases of a remediation project. You'll also see that there are boxes for other types of information, the project name, the project number, other names of people that are associated with the project, including, if you look at the central column and my cursor, a reviewer, someone who is going to have the final look at all the information in the checklist and be able to say that, yes, everything makes sense, this project can move forward. These boxes below here are actually signature boxes. The way we use this tool is that when we are in agreement on the responses to various tasks that we outline or statements that we make, we sign off with our initials in these boxes, and we create then our project planning tool. Now, we use a variety of information in the select category, in the design category, in the execute category, and that information is set up to get us to think. So look, for example, as we look at this right column, and the first line item says remedial objectives have been clearly defined. So that's a key point for us. We have to understand what it is we're trying to remediate, what are the goals of our remediation. So everyone on the project team must be aware and must understand what those objectives are. And then we drop down to the next category and we try to understand, what are the site closure barriers? What are obstacles that are going to get in the way of us performing to the level that we need to on a remediation project? And you can see there's other types of information that's required. And we have over 20 different statements in this checklist that allows us to consider different aspects of the project. Someone will ask, can I have a copy of this checklist? And the answer is yes, I will make one available for you after this webinar. I'll provide that to Gareth, and you can have the checklist and customize it in whatever way you want. But this has become a very useful and a very important tool with everything we do. So when you have a site that looks like that, what you see on that screen, that series of lines there, that's all the subsurface infrastructure that one might encounter on a project. This happens to be a filling station, a gas station in the US. It's a site where we have a lot of underground utilities. There's nothing overhead. Look at some of the other things that we see on the site. If you go to the top of the screen and follow my cursor, there's a planter up there. That's an important piece of information. There are plants and trees located there. And that's something to consider again, if we're going to be injecting something at the site, what impact will that injection have on those plants and trees? So by looking at this figure on the screen, you can pick out different things that are going to be of significance for your project. Notice to the right of the screen that there's a driveway and a sidewalk. So that tells me there are going to be vehicles that can be entering the site. That tells me there can be pedestrians that will be near the site, and we need to take that into consideration. You'll also notice I have several different colored dots on the screen, green and red. Those are all injection points, or blue. These are all points that have been placed at various times, injections that have been made at this site. And notice how they work around all of this infrastructure. You'll lastly notice that I have a grid on the site, letters to the left, numbers to the bottom of the screen. And basically I use that grid superimposed on the figure of my site to be able to identify specific locations for injection. You can see that I may have a point at K11, this green point to the left of the screen, K11. And this is a helpful means also to set up your injection project. When you're ready to go to the field, you can tell the field crew that today we're injecting points K11, K17, K21. It makes for a nice means by which to instruct the field crew and also keep track of where injection points have been placed across the site. So note that from this figure as well. So another one of our sites, this comes from our colleagues in Belgium. And this is a remediation site that they completed with Regenesis, some pilot testing that was done with chlorinated solvents and using HRC bioamendment in conjunction with plume stop. And you'll notice that the injection locations here are on the perimeter of the building. You notice there are also not really many points located within the building. And oftentimes that's the best we can do on a site, is be able to work on the periphery of a facility, unable to get inside to address all the issues underneath the building, but we can do our best by working around it. And of course, we look around the building for things like drains or other types of discharge points that can be key sources of contamination and places that we need to address with our remediation. So studying our figure can tell us a lot of information. It's another example of a site, again, going back to a filling station and looking at some of the placement of injection points around some of the infrastructure, the canopy, the garage area of the site, well away from the tank area. And again, this gives you a sense of the layout and some of the things that one has to consider on a site, things that we have to avoid, but yet at the same time, we still need to find areas in which we can inject our remediation chemicals and make the remediation as successful as we possibly can. So again, the picture tells us a lot of information. Here's an actual field photo of that site from our colleagues in Belgium. And you'll notice the setup here. We're working in a very narrow area. If you look in the distance, you will see it appears there's a truck that perhaps passes through that area, that alleyway, frequently. So that's a consideration and an important safety point in what we do. Notice that the injection is taking place very, very close to the building. And also notice that there, to the bottom of the screen, that there's a manhole cover. So that tells me there's a sewer or water utility that's in proximity to where the work is being done. These are important considerations. Also, there are a row of trees on the side of the site. And this row of trees can be very important too, since we're doing injections. If we were to have chemicals that surface over here by these trees, we need to understand what's going to happen there. Is there going to be some damage to those trees? Is there going to be a problem or an issue because chemical may have found its way over to that vegetation? So these are very, very important points, and it just helps us with our project awareness and our thinking. So now I'm going to go on to the very first part of the checklist, which is selecting technology. It's very, very important to find the right technology, or even better so, combinations of technologies that will do the best job, that will help us meet our remediation objective in the best way. Most important thing you can do is learn about your site. Know as much as you can about the subsurface. Certainly have a reasonable estimate of how much contaminant mass is present in the groundwater, how much contaminant mass is sorbed onto the soils, and how much contaminant mass may be present as free phase. That may be light non-aqueous phase liquid, or LNAPL, when a petroleum product is part of the contamination. It may be dense non-aqueous phase liquid, or DNAPL, when chlorinated solvents are part of the issue. So knowing these things, knowing where they exist within the subsurface, knowing the source, and oftentimes we don't know the source. We're on a hunt to try to find those things. These are all critical pieces of information as we now work towards selecting a technology for our site. We also need to know if our contaminant plume resides only on our site, or if it has worked and migrated and found its way off-site to other properties. That opens up a whole new series of issues, and something we want to know as we go in and we plan our project. And of course, the most important thing on a project is to develop a good site conceptual model. Some people say conceptual site model. So SCM or CSM, call it what you will, but the important thing is to have a conceptual site model. And that basically means you need to collect information. And that information all feeds the model. So what is the model? The model is a description of the site, but even more so, it's a visualization of the issues at a site. Someone once said to me that the best conceptual site model is when one can take all the complexities of the site and all the information and boil it down to a simple picture or a simple cartoon to tell the story of the site. And a conceptual site model is dynamic. You start with a site model and then you can build on it as you develop new information. Where you initially started with your conceptual site model may change as you get more and more information, and it may look considerably different than where it started. But the conceptual site model is a very important aspect of developing the plan for the site, just knowing all the different aspects of what you need to do and the issues that you need to consider on the site. Of course, it's the best input in leads to the best site conceptual model. The collection of field parameters is very important. And regardless of whether you collect field parameters, those are things like conductivity, pH, temperature, oxidation reduction potential, better known as ORP, dissolved oxygen, better known as DO. Whether you do that with a probe, or if you do that with a flow-through cell, or even if you do that with a test kit, it's very, very important that the person collecting those data do calibrations properly, that they carefully look at the data they're getting to make sure that the data makes sense given the site considerations. And it's also important that the person collecting the field parameters is experienced or has someone with them that is experienced collecting these type of data. These data are going to be important because they're going to feed into your conceptual site model. So the more accuracy that can be built in, the better the site conceptual model will be. It's also important to know the geochemistry on a site. You know, most times we certainly go out and we collect field parameters, we collect our contaminant data, but do we always collect geochemical data? Do we know how much nitrate is in the groundwater, or manganese, or iron, or sulfate? Do we evaluate carbon dioxide and methane? You know, these are all part of the complex chemistry of the subsurface. And that type of information tells us a lot, again, about what sort of condition that the site is under. Is it a site that is aerobic and has a lot of oxygen present? Or is it an anaerobic site or an anoxic site that has very little oxygen present? And how does that match up with my contaminants then and how they degrade and the chemistries that I might apply to that site for remediation? So collecting geochemical data is a very important step as well. And it's also important in that these data feed the conceptual site model. So if you collect field parameters and geochemistry, you're going to have a wealth of information to make decisions on selecting technology. Since I'm a microbiologist, I always have to put in a good plug for using molecular biological tools on a site or some sort of data collection to understand the microbiology. Now, you may not do a bioremediation technology for the site, but you might want to know the information anyway, so that further down the road, if you're considering combinations of technology, bioremediation may come into play somewhere along the project. And there's so many different sampling techniques that are available now to collect good microbiological data. The picture on the left has a device called a biotrap that's inserted into a well. It resides there for 30 to 45 days. It has specialized little Nomex beads in it, and the microbes basically take up residence on those beads. You pull the biotrap out of the well, send it to the laboratory, and they analyze the beads that are on the trap by a variety of methods that are listed in the box to the right. And you get a lot of information on the types of microbes that are present. You might understand some of the enzymes they produce or the gene functions that they utilize to break down different types of contaminants. And some of those analyses listed in the box to the right also will tell you for certain whether degradation is actually occurring. There's also another way to sample. In the picture in the center, you will see the sample technician is actually looking at using a filter. And this is another way to collect a sample for microbial evaluation. So if at all possible, if budget allows and time allows, I would certainly encourage you to collect samples for microbiological evaluation with whatever vendor that you choose to work with to get that sort of analysis done. But again, that's another important piece of information that will fit into our site conceptual model. And of course, in 2018, we have many different types of field tools that we can utilize, different types of instrumentation, the membrane interface probe, hydraulic profile testing, water injection tests. We have so many tools at our disposal that can help us understand the very detailed stratigraphy of the subsurface, the very detailed transmissive versus non-transmissive zones in the subsurface. These are very important characteristics. There's really no reason not to collect those data. They will just simply make your remediation project better. They will make the selection of remediation technology better. And by all means, certainly look at photographs of your site. If you don't have the opportunity to go to the site you're remediating right away, look at photographs, look at historical photographs, look at all the things that have gone on at the site, because it tells you very important information, again, that will help you make your technology selection. So use the tools that are available out there. Then, of course, the star of the show is always the chemistry. The chemistry is what's going to get you to your end result. Now, many of you may have experience with different Regenesis products. I've been fortunate to have used the entire array of products at one time or another. And I like using them in combination. And I find that there are often times where I'm using 2 or 3 different Regenesis remediation projects in my products in my project. Now, Regenox Part A is a very interesting chemistry that I like. We sometimes use a little bit of Regenox Part A as part of our bioremediation. It happens to be a very good desorption chemical, in addition to being a very fine oxidant. So Regenox Part A has a role not only in our chemical oxidation projects, but also in our bioremediation projects. It has an alkaline chemistry associated with it that does a very nice job of scrubbing soil and taking off some of that sorb phase contaminant and allowing it to be placed into the groundwater where it can be more readily remediated. Persulfox is another fine chemistry, a strong oxidant that will leave behind a little bit of a sulfate trail. I like it in that it can be used across a wide range of pH. And also with that sulfate release at the tail end, you can actually stimulate some anaerobic bioremediation, which may be very useful on a petroleum site. So it's important to know the characteristics of the remediation chemicals that you're applying so that you get all of the advantages of those chemistries as you apply them on your remediation site. And then there are other products. There's oxygen release compound, advanced, or ORCA. That is one that has been tried and true for years and years, and one that allows you to increase the dissolved oxygen at a site and achieve degradation of contaminants that degrade under aerobic conditions. Now, PlumeStop is a relative newcomer to the array of technologies provided by Regenesis, but PlumeStop is a liquid activated carbon material that has specially formulated that acts to retard plume migration. When it's placed in the subsurface, you can almost look like it as painting the subsurface and allowing the contaminants to attach to this PlumeStop surface, where in turn they're fed a bioamendment and biodegradation takes place on the interface between the PlumeStop and the contaminant and the water that attaches to that carbon particle. So very interesting chemistries, and these are the tools, the technologies that we're evaluating as we're trying to select technologies for our site. Now we get into the design aspect, and designing a remediation project, again, is all based on information. Some vendors have design software that you can use and access. I would certainly encourage you, if you're not already doing so, if you're going to do a remediation project with Regenesis, that you engage in multiple calls and discuss the site in great detail. Don't just send them a report or send them a figure or send them a table of data, but in fact, talk with them and strategize together. We find that that promotes the best possible project. By all means, attempt to calculate the mass that's present, not only in the groundwater, but also in the soil. So you need to invest in sampling within the soil matrix, as that will help your mass calculations, help you better understand how much mass is present, so you can get the proper stoichiometry of remediation chemistry in place to meet your remedial objectives. Again, I mentioned, look at photos of the site, visit the site. You'll notice in the photo to the left that there are many markings on the surface. Some of those are utilities that we found and need to avoid. Some of those are actual locations where we're going to place injection points. And it's good to mark those out with paint, with flags, some way to designate that those are going to be the injection locations. So then, as we consider our design for a remediation project, we also want to think how we're going to distribute our material. What sort of technique are we going to use? Are we going to use an injection well? And if that's the case, then we need to understand what sort of screen length we want on our injection well. Or are we going to use direct push technology and we're going to inject across a very specific vertical interval? I find people often make the mistake that they want to inject across the entire screen length of a monitoring well. And if you have sufficient information on your site, you may well learn that that is not necessary. Again, keep in mind, you want to put remediation chemistry in a place where it's going to do the most good. And that means distributing that chemistry in the areas where the contaminant mass is found. So if our contaminant mass is from 7 to 9 meters below ground surface, that's our target. But our well stream might be longer than that, but there's no need to supply chemistry to a greater vertical interval than that, because that chemistry will not do any good across that entire interval. So put the chemistry where the contaminant mass resides and where it is transporting at the site. So understanding the flow of groundwater, how fast is it moving, what direction is it moving, those are all critical portions of your design. And then lastly, what do you have to work around on a site? What are the structures, the infrastructure in the subsurface that are going to get in the way of your injection? What infrastructure is present that is sensitive to the chemistry, where there might be a adverse effect if the chemistry contacts that infrastructure? Those things are very important to know, and yet we still have to get the proper placement of injection wells or direct push points on our site to get the best result. But all those things need to be considered. Of course, you can do bench testing as part of your design. I've seen it in Europe perhaps more so than in the US recently. We don't do quite as much bench testing as we once did. I don't know exactly why that's the case, but we've gone away from some of the bench testing that used to be very standard on a lot of our sites. But always, if you're doing chemical oxidation, I would encourage you to do an oxidant demand test on a sample of soil that is outside the area that you need to treat. I would pull a sample of just the natural soil from the site, submit it for oxidant demand testing with the specific oxidant that you're going to use for the site, whether that be Regenox or whether that be Persulfox. It's very, very important that the oxidant demand test be done with the actual oxidant that's going to be used. That gives you a piece of information as to how much oxygen will be wasted on the natural soil itself. And then you have to factor in the contaminants that are present, and also the fact that the oxidant often will consume itself. So those are very important things that are part of oxidant testing. And then lastly, there are different types of jar tests to simulate field conditions to the extent possible, or column tests, as you see in the photo to the right. These can give you good information on distribution and also on just characteristics of how certain chemistries will react given the actual matrix that you're going to inject into. Do the best you can creating soil to groundwater ratios that mimic field conditions as best as possible. It's very, very difficult to do in the laboratory to simulate that condition, but I know that the ratios have changed more and more as testing has evolved, and we're able to do better quality bench tests now than we once did. And of course, use the stratigraphic information that you get. Look at the zones that store contaminant mass. Look at the zones of highest permeability. And you can see here on this particular figure that there are sand zones that are identified. And these would be zones in which the contaminant would travel. There may be much tighter zones, perhaps clays or silts, that are found at the site where the actual contaminant may diffuse into the clay. So it may be necessary not only to put remediation chemistry as part of your design into these sand zones, but you may need to put it up against some of the clays as well, so you can account for the matrix diffusion. So when contaminant is squeezing in and squeezing out, you have some treatment there to address that. Okay, and lastly, now we've gone through selecting technologies and considerations there, and then designing a remediation project. Now we're going into the execute phase of our project. And basically, again, it starts with a good understanding of what is the area that I need to inject. If you look at this figure, I've got both some vertical information on here that tells us something about the depth that we're going to inject, but then I also have a two-dimensional look that kind of evaluates, where is my plume? What are the main areas that I need to remediate? So the execution starts with that aspect of it, knowing the location and the area that I'm going to treat. And then it goes through a series of questions that are all part of a checklist that we talked about earlier. The first one being, is my injection subcontractor up to speed on the project? In other words, do they understand as much about the project as you do? Do they really have a good appreciation for the goals and for the safety aspects of the project? So that's an important question to ask and answer. How about site access? Is there an easy way to get the injection equipment and the chemicals to the site? Is there an easy access in? Is there a secure fence around the property? Is there a gravel road in, or some area that's not paved that has to be a consideration if the weather is bad? Those are key considerations. Looking at the box in the bottom left, do I have a health and safety plan for my site? And I absolutely should. And is it specific? Does it talk about the issues that are specific to that site, the chemistries that are going to be used to remediate the site, the techniques that are going to be used? All that has to be addressed in the health and safety plan. Have you visited the site? Have you taken photos? And are you prepared to take photos throughout the injection process, as well as even after the injection process is complete? Because you want to document that for your project. So not only do you have field notes, but you have field photos as well that document the activities that take place. And then lastly, are all your required permits in place for your remediation? Are there injection permits you need? Are there any sort of discharge permits? Are there air permits? Are there any other types of unique permits that are required at the particular location that you're injecting? How about, does my site have ground cover or not? What is the integrity of that cover? Well, that question means, does your site cover? Is it covered with asphalt or concrete or some other hardened surface that will prevent rainwater or snow from infiltrating down into the contaminated zone and bringing more contamination to the groundwater? And what is the condition of that surface? Is it new and solid, or is it broken up with many cracks in it? And will it allow water to permeate it? Very critical question. Again, we've talked about infrastructure, knowing what's beneath the ground, but also what's above us. You know, are we going to be able to get our direct push equipment underneath a series of lines that are above us? Or do we have to stand away from those a distance or move our injection points because we simply can't get underneath them? How about storm sewers present? Those are things that we need to consider, because if we have a spill or if we have surfacing of our injection chemicals, we need to protect the storm sewers to keep those surface material from finding its way to the sewer. How about vegetation? What's around? If remediation chemistry finds its way to the surface or to the root zone of plants and trees, you may have an adverse effect. You may have a situation where those plants or those trees will perish. What else do you notice about adjacent properties, the neighboring properties? What goes on there? What sort of activities are going on? May they have some impact on the work that you're doing? And then how about traffic? What's the pedestrian traffic look like? And what do the vehicles look like that are coming in and out of the site? You need to take those things into consideration. How about injection specifics? If you look at the photo on the left here, you can see a setup for an injection. You can see the direct push rods that are connected to a series of lines. Notice the lines that are on the ground. This happens to be a concrete surface that's in relatively good shape. But as all part of the execution, you have to consider the number of injection points or wells. How many injection events will you have, which means how many times will you come to the site and inject a remediation chemical? Once? Probably not. Twice? Maybe so. 3 times or 4 times? That's probably more realistic. What is your injection interval? Do you use a technique where you start at the bottom of your interval and work up? Or do you start from the top and work down? What is the volume that you will inject? And then, do you use more volume and less points, or more points and less volume? Those are key considerations based on the geology of a site and how we can best distribute our fluid on the site. How about spacing? How far apart do our injection locations need to be? 1 meter, 2 meters, 5 meters? It's all driven by groundwater movement, by the soil permeability that you have at a site. How about daylighting? You'll notice the picture to the right. That is an example of, in the red circle, of material that has daylighted, that has come up out of the ground. We want that material to stay in the ground so it can help us achieve our remedial objective. But realistically, at every site, there is some level of surfacing or daylighting that occurs. And there's an example of it right there. It's come up from a crack in the concrete. It's very important that you receive an injection report from your contractor. When I work with Regenesis, I always get a table that looks like this. It tells me the time at which an injection took place at a specific location, the depths that I'm working in, the pressure that I'm working under. I like low pressure and low flow as the best way to distribute remediation chemicals. Again, the rate at which work is conducted, the interval, and of course, any unique notes from field activity that can be helpful in evaluating the data. So pressure and flow, I would say, are the 2 most critical aspects of controlling distribution of remediation chemicals in the subsurface at a site. We're going to finish up with a little bit of safety here, and then we should have some time for questions. This little octagon is something I use to consider all the different aspects of safety. We're going to touch on 6 of them very quickly, and we're going to skip biological and radiation today. But these are things just to consider as you go about planning your site and considering the safety aspects. Think about the chemicals. The biggest advice I can give you is read the safety data sheet on the chemistry that you're bringing to the site. So if you're going to inject persulfox on your site, read the safety data sheet, understand the characteristics of the chemical, understand what it does, understand where your personal risks are with it, also understand how you might clean it up if there is a spill at the surface. My big lesson here is respect the chemical as it says in the red lettering at the bottom of the slide. Transporting chemicals. When one needs to bring chemicals to the site, it's important that someone who is properly registered, that has the proper credentialing and certifications, be the one that delivers that material to the site. And also move it around the site. It has to be moved by people that are used to moving remediation chemicals around. They have to have proper safety equipment and training. And it's very, very important that they are in line with all regulation. There's proper labeling and proper marking on remediation chemicals that come to a site. So no one should be moving or shipping chemicals to a site that doesn't have the proper credentials. Handling and application, that's very important that you wear the proper safety equipment. Most time there's some type of coverall, certainly gloves and steel-toed shoes, safety glasses at a minimum, and often a face shield that will protect you from splashing when liquid chemicals are being used. It's also very, very important to have an eye wash station. I know here in the US, we've worked with Regenesis and their field crews to have an eye wash station mounted on the side of the injection vehicle, so that in case there is an accident where liquid chemical has splashed into someone's face or on their skin, that they have an ability to have 15 minutes of continuous flow to wash that material off. So having an eye wash station is very, very important as part of the safety aspect of your project. Storage, lesson here is never store chemicals of any type in containers that are not compatible. So if you have extra chemical left from an injection project, make sure they're stored in the proper container. Often polyethylene drums are suitable, usually not a steel drum. Usually a steel drum will create issues with corrosion and other types of reactions. So it's important to know what sort of container you can put excess material into if you need to store it on site for any reason. Keep in mind that chemicals are reactive also, so you have to think of compatibility. When you're injecting something into the ground or it comes to the surface and contacts something, it's very, very important to know what the compatibility will be. And I know here in the US, it's a big issue. It may also be in Europe that we also speak to the local fire department when we're doing an injection project, especially with chemical oxidants, that we notify them that these types of chemicals will be present on our site. And oftentimes that's just simply a conversation, and they're just glad to know that in case they should have to respond to an incident, that they're aware of the situation and how much material we have on the site. Spills and releases, we've talked about that before. Spills, releases, they are a fact of life on site. They do happen. We like to see the most minimal amount of surfacing as possible at a site, but if we do have a more significant spill, the solution is most often lots and lots and lots of water. Some say a rule of thumb is 20 times as much water as the size of the spill in order to dilute it and wash it down. And you can use booms and other sorts of equipment to help prevent leakage or movement of surfacing away from an individual injection point. Disposal, if you should happen to need to dispose of any sort of remediation chemical, you need to understand its characteristics. The best lesson here should be only mix up as much remediation chemical as you know you can inject. Don't create an excess and create a disposal situation for yourself. So use batches that you know you can inject, use batches of remediation chemical that you know you will use by the end of the workday, so that you don't get into this issue of storage and disposal, because that can be a significant problem, especially when the stored material has very high or very low pH. Pressure is very important. Most of our injections are done under pressure. So we need to make sure that all of our equipment is in good condition and that we are able to test it in advance with water to make sure there are no leaks, that it's clean, and that we use a rule of thumb that a minimum of 150% of the operating pressure is the rating for the various lines and equipment that we use on our site. And we have a device, as you see in the circle here, called whip checks that we use on the hoses and lines that are part of a remediation injection to keep them from moving around as pressure comes through them. So those are very helpful. Always be aware of slips and trips on sites. If chemical does spill on the ground, it's important to clean it up quickly so that no one moves through it and slips. It's also important to be aware of all the different lines that are on the ground. You may be injecting at multiple locations at one time, so there's a lot of lines that are on the ground, a lot of hoses. There may be open well covers, as you see in the photo on the bottom, and these are all things to consider. Gravity, if you're lifting, especially be aware of lifting properly and being able to be careful, especially when you're taking things from overhead. Sometimes we inject with gravity, and that requires us to put our mixing tank up above us and feed from up above our heads. And we have to be very careful how we stage that and be cognizant of the weight of those particular mixing units. So very, very important as well. Be sensitive to hot and cold and conditions. Hot and cold also applies to the chemistry, especially if you're working in winter conditions. The water is obviously very cold. That's one consideration. But also be aware that if you're using chemical oxidants, they can generate heat. And that has to be a consideration in your work as well, and the types of safety equipment that you use. Electrical, we've talked about that a bit as well. Always be aware of electrical sources that are present. Be aware that we don't contact them with any sort of injected oxidant. Maybe necessary to have them shut down prior to an injection project, or use some sort of a lockout tagout procedure so that people are aware that there is electric that is present in proximity to where we're doing our work. So lastly, before we take some questions, I can't overemphasize monitoring. Monitoring is probably one of the most important things you'll do after the injection. It's important to monitor while you're in the field. It's also important to monitor at set times after the chemistry is in the ground. You want to make sure that you monitor your groundwater wells or collect soil samples at a time point where you won't miss some of the main activity from your remediation chemistry. If you're doing multiple injections, then you have to plan for that down the road as well, and multiple sampling events. And then I'll leave you with, always use proper personal protective equipment. Always make sure your sampling equipment is in good order. One thing I found is that when one applies remediation chemistry to a site, a very important time frame is 14 to 60 days after the chemistry is in place. Those are periods, that's a period of time where there's a lot of activity, and it's very, very important to at least collect one, if not more, samples in that period of time. Also, if you're using oxidant, beware that that oxidant may find its way directly into a monitoring well. And the next time you sample that well, you may have a very high or very low pH. So all that has to be considered as part of your safety protocol for a project. So in summary, before we take some questions, the lessons learned here today. Robust data collection is necessary. The more data, the better quality data you can collect, the better your project is going to be, the more successful. Be prepared. The more prepared, perhaps by using the checklist that I've talked about, the more planning that you do, the better your project will be. Field awareness keeps everyone safe. Be aware of the things going on around you. And then lastly, be open-minded to various options, combinations of technologies. All these things can be helpful in achieving the performance you want on your site and saving money in the process. And with that, again, I thank you for your attention, and I thank Regenesis for hosting this webinar. I'll be glad to take questions.
Thanks, Jack. That was fantastic. That was really interesting. Thank you. We have got about 10 minutes to answer a few questions. So we have got a number that have come in, but if you've been waiting to this point, now's your chance. Please put questions in the chat panel, and we'll do our best to answer them. And if we don't get round to them, we'll answer those questions via email afterwards. But while we're waiting for further questions to come in, Jack, if I could ask a couple of questions. The project checklist, I think, is fantastic. When do you first reach for that in a project? While you're doing the site investigation, when the go-ahead's been given, when is it that you're first starting to think about the data that you're going to capture on that checklist?
We use the project checklist immediately after we have our site investigation. Data have come in. When we know that there will be some sort of remediation that will be required, that is our cue that we need to begin the checklist. And we do it in stages. We start with that selection phase because that is well suited to that early data that's collected. And then we just build on it from there as we move through the project.
So it's a live document where it allows gap analysis as you're moving forward?
That's exactly right. It's a live document. It allows placing notes within it. It allows people to react to the notes. And then once everyone is in agreement, then they sign off on that particular aspect of it, and they continue to work their way through the checklist. It is a very useful tool.
And just thinking about, usually on a project, we're not lucky enough as consultants to be given a blank check to do all the site investigation we want.
Yes.
Is there what would you start with? What's the minimum amount of geological or geochemical data that you would look for, and then what would you add in as you move forward to add precision, accuracy, and granularity to designing an injection method, an injection project?
Yes, well, obviously the chemicals of concern, the target contaminants, would always be available. Those data would certainly be absolutely necessary. Then the field parameters are easy to collect. They will at least give us some basic information. And again, that's the conductivity, the pH, the temperature, the ORP, the dissolved oxygen. If you only have a minimal budget, you don't have the budget to do the microbial or a wide suite of geochemistry, I would get at least nitrate, iron, that is total and dissolved iron, and I would get sulfate, and then probably methane. If you can get those things at a medium, that will allow a general characterization of the site, and you can work with that to develop a design. But then you can build on it with additional parameters, geochemical parameters, as well as the microbial.
And for larger or more complex sites, do you ever do pilot testing on a small part of the site?
Yes, absolutely. Pilot testing, in my mind, has replaced a lot of the bench testing we did years ago.
Sure.
I think we've seen many pilot tests where you even consider it a phase of the overall remediation, where the pilot test is conducted in an area of the site, and then it's duplicated in additional phases as you move through the site. So you can look at it in different ways. You can look at it as a means by which to get answers for some troubling issues at a site, but you can also look at it as the first phase of the remediation, and then just keep going.
You mentioned microbial testing, and there's a number of tools that you can use. How important do you find that for a project where potentially you're going to go in and manipulate that redox? So what is it telling you at baseline, or are you setting yourself up to then learn more as the remediation project goes forwards?
Yeah, I think the microbial, again, selfishly as a microbiologist, I place a lot of value in the microbiology. It's good to know what's there, but it's good to know what's not there, because the microbes are tools as part of the remediation, and they can be very beneficial. They also can be detrimental. You know, they can use up a lot of dissolved oxygen that may be very valuable in the degradation of your contaminants. You want the right types of bacteria that are working on your particular contaminant type. And then it's nice to be able to track them as the remedial process progresses, because if you can see an increase in their numbers, if you can see an increase in their functionality, then you can say, you know, I have another piece of evidence here that my remediation performance is optimal.
Sure, to create the entire picture.
Absolutely.
In terms of variability then, if you're doing microbial testing, how much would you want to do on the site? And would you have testing in control areas outside of your suspected plumes? How would you deploy that?
Yes, you certainly want to go to a control area, something that's outside the plume, so you can get a sense of what the natural microbiology is at the site. Then I would say at a minimum, you want to go to perhaps one of the most highly contaminated areas of the site and collect a microbial sample there. And then one perhaps that's not quite as contaminated. Also within the plume, but not as contaminated. And that makes for at least a good comparison. Of course, if you can do 4 or 5 or 6 or 7 wells, that just adds to the information. It allows you to make a broader evaluation of what's going on. And there can be, many sites have sort of general microbial characteristics for the site, but there are some very specific things that can be going on a microbiological basis at individual wells. So it's good to know that.
Mm. And as well as the microbial populations that will be changing with redox manipulation, with using chemical oxidants, etc., somebody's asked a question about whether the consideration is made for potential knock-on effects for redox-sensitive metals, etc. So you try to fix one problem, potentially you cause another. Is that captured within the project checklist? Is that something that's discussed beforehand?
It absolutely is, and it is a valid concern. I mean, metals are a key issue for us. Whenever you're manipulating the redox, you're certainly going to have an effect on metals. Now, I guess what I've seen through all the years of remediation is that those effects stay very localized within the locations of injection, and that they don't move very much. The impact is not felt very far beyond that. And I found that typically the metals concentrations will return to background levels within months, not years, months, post-injection.
Sure. That leads on to a second question we got about if you are doing remediation near surface water, and the example they gave us within 100 meters or 100 yards of surface water. Again, is that something that is fed into the checklist for concerns? I mean, perhaps 100 meters is quite far, but if we assume there's surface water adjacent to the site, again, is that something that's taken into account?
Absolutely, and that's all part of that site awareness that I spoke about, looking at the features that encompass the site and understanding, we see strange things on sites very often where we anticipate a chemical to go. It doesn't always go to that exact location. And we see unique scenarios where a chemical travels much, much greater distance than what we had assumed for any of a number of reasons. And so a surface water feature like that would be something we'd consider. We'd probably sample the surface water before and after. And it's absolutely noted in the checklist and an important feature.
Okay. And just thinking about practicalities, during injection on site, what are the most common issues that you come across when trying to complete injection at site?
Yeah, I think the most significant things that we see on sites, oftentimes it's issues with the equipment, refusal at a particular location, and a need to quickly change the injection location because we can't inject at that specific location. The other major issue is surfacing, not so much around the wells, but at places where we didn't anticipate, which is why it's very important for the field technicians to be looking around the site and identifying locations where potentially something is seeping from the ground, finding its way through a crack at the surface, and that's where your daylighting occurs. So that too is a very important issue.
Right. And as a final question, someone's asked what informs the decision on injection approach. You showed direct push injection, and I know we talked about injection on wells, but are there situations where you reach for something like soil mixing, and how would you make that decision?
Yeah, definitely. If I'm in a less permeable scenario, if I have a lot of clays and a lot of silts, I may desire to mix that as opposed to inject into it. So that's one scenario. I like direct push whenever I can use it, but we may have depth limitations. that don't allow us to use that technique. I like direct push in that you can target some very specific zones with the tooling. But I like wells when we know that we're going to come back to the site for multiple injection events. And so wells can make a lot of sense under that scenario, and to be able to get more volume in and get greater distribution. So it really depends on the site-specific conditions, the ability to get back to the site on a regular basis. All those things come into play as we're making that consideration.
Okay, perfect. Thank you, Jack. That was really informative. I really did enjoy that. I'll let you go and catch your flight. I know that you've got a busy day ahead of you. I'd just like to say we're going to send a follow-up email to everyone just to ask for some feedback. If you could please fill that in and let us know how we can continue to improve, that would be really useful. You can get a CPD certificate for this. If you fill in the form and send it back to us, we can send that to you as well. And we will send out a link for the webinar recording once that becomes available. But thank you, Jack, once again, and thank you everyone for joining us.
Thank you, everyone.